Hi everyone, welcome to One Stop Mathematical Solution. Today we are going to solve CSIR NET Mathematics December 2011 question paper. In this video we have only dealt with the complex analysis part. First question, question 22. Consider the power series sigma n greater than or equal to 1 a n z power n, where n is the number of divisors of n power 50. Then the radius of convergence of sigma n greater than or equal to 1 a n z power n is. So we are given a power series here and its coefficient is defined by this. Then we have to find its radius of convergence. So first of all, we'll look into the concepts used. We know for a power series, sigma n is equal to 0 to infinity a n z minus z naught whole power n. The radius of convergence r is given by the formula 1 by r is equal to limit n tends to infinity modulus a n whole power 1 by n, or 1 by r is equal to limit n tends to infinity modulus a n by a n plus 1. And if n is equal to n1 per alpha 1, n2 per alpha 2, etc. up to nk per alpha k, then the number of divisors of n is given by the formula tau of n, which is equal to alpha 1 plus 1 into alpha 2 plus 1, etc. up to alpha k plus 1. Essentially, tau of n will be a natural number. So now we'll move on to the question. So they have given an to be the number of divisors of n power 50. So an is essentially a natural number which is greater than 1 and less than n power 50. Therefore, our radius of convergence of the power series is given by 1 by r is equal to limit n tends to infinity modulus m power 1 by n. So when we apply the limits, we will get m power 1 by infinity, that is m power 0. So anything raised to 0 is equal to 1. So we got 1 by r is equal to 1. Therefore r is equal to 1. So we will check the correct option. So the correct option is 1. Next question, question 35. Let IR is equal to integral over CR dz by z into z minus 1 into z minus 2, where CR is equal to set of all z in C such that mod z is equal to R, where R is greater than 0. Then, so we have defined an integral value here. We have to check which of the following option is true. So first of all, we look into the concepts used. The singularities are obtained by equating denominator to the 0. Cauchy integral formula states that if z0 lies inside C, then integral over z f of z dz by z minus z0 is equal to 2 pi I f of z0. If z0 lies outside C, the integral value will be 0. F of z has pole at z0. If limit z tends to z0, f of z is equal to infinity. F of z has pole of order m. If limit z tends to z0, z minus z0 whole power m, f of z exists and is finite non-zero number. F of z has pole of order m at z is equal to z0. Then residue of f of z at z0 is given by the formula 1 by m minus 1 factorial limit z tends to z0 dm minus 1 by dz power n minus 1 z minus z0 whole power m f of z. And Cauchy residue theorem says that if a function is analytic within and on C except at finite number of isolated singularities z1, z2, etc. up to z0, then integral over z f of z dz is equal to 2 pi I sigma k equal to 1 to n residue of f of s at zx. So this question can be done in two ways. One is like using Cauchy integral formula and another is like using Cauchy residue theorem. I have done both the ways and I will show you how to do that. So now we'll move on to the questions. So they have given IR and CR is defined like this. So using Cauchy integral formula, first of all I am splitting the given function using partial fractions. So 1 by z into z minus 1 into z minus 2 can be written as 1 by 2z minus 1 by z minus 1 plus 1 by 2z minus 2. Therefore, IR is equal to integral over CR 1 by 2z minus integral over CR 1 by z minus 1 plus integral over CR 1 by 2 into z minus 2. So singularity is obtained by equating the denominator to 0. So I am equating the denominator to 0 and I got z is equal to 0, 1, 2 as the singularity. So we will check option wise. So first option is IR is equal to 2 pi I if R element of 2, 3. So I am taking some approximate R value is like 2.5. If R is 2.5, then all singularities lies inside CR. Therefore, using Cauchy integral formula, we get IR is equal to 2 pi I 1 by 2 f of 0 minus f of 1 plus 1 by 2 f of 2. So when we substitute the values, we'll get is equal to 2 pi I into 1 by 2 minus 1 plus 1 by 2. So the value we are getting is equal to 0. So when R lies between this interval, IR we are getting as 0. So option 1 is not true. So second option, IR is equal to 1 by 2 if R is element of 0, 1. So I'm taking R is equal to 0.5 and checking whether IR value is 1 by 2 or not. So when R is equal to 0.5, we only get z equal to 0 only z equal to 0 lies inside the curve CR. So all other integral value becomes 0 by using Cauchy integral formula. Therefore, we will get IR is equal to 2 pi I into 1 by 2, that is equal to pi I. So we are not getting the same value. So now we'll check the third option. IR is equal to minus 2 pi I if R element of 1, 2. So if I take R is equal to 1.5, we'll get only the singularity 0 and 1 lies inside such a curve, and the singularity z equal to 2 lies outside. So this integral value becomes 0. Only these two integral value we are taking. So this is equal to 2 pi I into 1 by 2 minus 1. So we'll get minus pi I. So we are not getting the same answer. So this is not true. IR is equal to 0 if R greater than 3. So I am taking R is equal to 3.5. Then all the singularities are coming. So when we take the Cauchy integral formula and apply, we'll get IR is equal to 2 pi I 1 by 2 minus 1 plus 1 by 2, that is equal to 0. So only the third option, only the last option is coming. So now if we use the Cauchy residue theorem, first of all find the singularities equating the denominator to 0. So we'll get z is equal to 0, 1, 2. Now find the residue of IR at 0, 1, 2 using this formula. So we'll get residue of IR at 0 is equal to limit z went to 0, z minus 0, 1 by z into z minus 1 is into z minus 2. So we'll get the value is 1 by 2. Similarly, find for residue of IR at 1 is equal to minus 1 and residue of IR at 2 is equal to 1 by 2. So now we will check options one by one. First option, IR is equal to 2 pi I if R element of 2, 3. So I am taking R is equal to 2.5. So if R is equal to 2.5, the singularities, all the singularities lies inside. So we got IR is equal to 2 pi I into summation of all the residues. So when we find that value, that is equal to 0, but we are getting an other than 2 pi I, so this option cannot happen. Now we will check the next options. IR is equal to 1 by 2 if R element of 0, 1. So if R is equal, so I am taking R is equal to 0.5, then only the singularity Z equal to 0 comes in. So we will only use this residue, first residue. So 2 pi I into 1 by 2. So we'll get answer as pi I. So it's different from 1 by 2. Similarly, find for third and fourth option. So we'll get only the last option as correct for using Cauchy residue theorem also. So you can use any one of these methods, whichever you find it easier. So we'll check the correct options. So the correct option is the fourth one. Next question 679. Let f be an entire function such that limit mod z tends to infinity, mod f of z is equal to infinity, then. So we are given an entire function which satisfies this limiting value. Now we want to find which of the following options are true. So we'll look into the concepts used. Z0 is 0 of f of z if f of z0 is equal to 0. F of z has pole at z0 if limit z tends to z0, f of z is equal to infinite. F of z has essential singularity at z0 if limit z0 tends to z0, f of z neither exists finitely nor infinitely. So now we'll move on to the question. So they have given that f of z in entire function should satisfy limit mod z tends to infinity f mod f of z is equal to infinite. So I have got that function as f of z is equal to z, and we find that z is equal to 0 is 0 of f of z. Therefore f of z, and it is only 0, so f of z has finite zeros. So they have also asked whether f of 1 by z has essential singularity or pole at z is equal to 0. So I am finding f of 1 by z, so that is equal to 1 by z. So I am finding its limiting value, limit z tends to 0, f of 1 by z. So here there is a mistake, actually it is 1, f of 1 by z. So I am substituting f of 1 by z, so that is equal to limit z tends to 0, 1 by z. So when I apply the limit, I am getting it as infinite. So if it is infinite, then z is equal to 0 is pole of f of z by this concept. So now we'll check the correct options. So we got f is a polynomial and f has finitely many zeros, and f of 1 by z has pole at 0. So options 3 and 4 are correct. Next question, question 80. Let G be holomorphic functions defined on A union D, where A is equal to set of all z in C such that 1 by 2 less than mod z less than 1, and D is equal to set of all z in C such that mod z minus 2 less than 1. Which of the following are correct? So we have given two holomorphic functions which are defined on these two unions. Then we have to find which of the following are correct. So first of all, we'll look into the concepts used. Note that set of all holomorphic functions on a domain is an integral domain. So domain means nothing but an open connected region. So first of all, I am gonna plot A and D on xy axis. So A is like 1 by 2 less than mod z less than 1, and D is like mod z minus 2 less than 1. So let us plot that. So when we plot, we are getting an annulus region for A, and D is an unit sphere with a radius less than 1 and center 2, 0. So A union D is nothing but this union of these two region, and we see that A is an domain because it is open and it is also connected, and D is also open and connected, but A union D is not connected, so it cannot be domain, because if we take a point in A and point in D, we cannot connect it through any polygonal path. So A union D is not a domain. So now we'll move on to the question. So that is what is written in the first three statements. So if we take f of z in g of z equal to 0 for all z in A union D, then we can state that f of z equal to f of z in g of z equal to 0 for all z in A, or f of z into g of z equal to 0 for all z in D by the concepts of union. Now see that A is a domain and f into g is again a holomorphic function. So set of holomorphic function on an domain forms an integral domain. So this implies f of z is equal to 0 or g of z equal to 0 for all z in A. And similarly for this z in D, we get f of z equal to 0 or g of z equal to 0 for all z in D. So if we see that A union D is not a domain, so f of z into g of z equal to 0 for all z in A union D doesn't implies that f of z equal to 0 for all z in A union D or g of z equal to 0 for all z in A union D. So now we'll check the correct options. So the correct options are A, B and C. Next question, question 81. Let f be a holomorphic function on D is equal to set of all z in C such that mod z less than 1 such that mod f of z less than or equal to 1. Define G from D to C by G of z is equal to f of z by G of z. If f of z element of D and z non-zero, f dash of 0 if z equal to 0. Which of the following are true? So we are given a holomorphic function and we have defined a function g here by this concept. Then we have to check which of the following options are true. So first of all, we'll look into the concepts used. So I use the Schwarz lemma here. If f of z is analytic in mod z less than 1 and mod f of z is less than or equal to 1 for every z in mod z less than 1, then we can say that mod f of z is less than or equal to mod z per n for mod z less than 1 and modulus fn of 0 is less than or equal to n factorial. So we'll move on to the question. So by Schwarz lemma we can say is that mod f of z is less than or equal to mod z per n. So in particular I am taking z equal to 0. So this implies mod f of 0 is less than or equal to 0. We know modulus value is positive. So this implies mod f of 0 is equal to 0. And also we will get that mod fn of 0 is less than or equal to n factorial. This implies if we take n is equal to 1, mod f dash of 0 is less than or equal to 1. So we are given g of z is equal to f of z by z if z element of D and z is non-zero and f dash of 0 if z equal to 0. So I am rewriting this function so that this is equal to f of z minus f of 0 by z minus 0. Here f of 0 is 0, so it doesn't change the value. So now I am taking limit. So limit z tends to 0, g of z is equal to limit z tends to 0, f of z minus f of 0 by z minus 0. This is nothing but f dash of z definition. So we got that g of 0 is equal to f dash of 0. Also for every z in D, g of z is equal to f dash of z. We got that f is already in the question they have given f is holomorphic. So f dash is also holomorphic. So this implies g of z is holomorphic in D. For z not equal to 0, mod g of z is equal to mod f of z by z, and we have got that mod f of z is less than equal to 1 and mod z is less than 1. So finally we will get mod g of z is less than or equal to 1. And for z is equal to 0, mod g of 0 is equal to mod f dash of 0, and we already got by Schwarz lemma this is less than or equal to 1. Therefore for any z in D, mod g of z is less than or equal to 1. So now we'll check the correct options. So the correct options are 1, 2 and 4. Next question, question 82. Let U be an open subset of C containing set of all z in C such that mod z less than 1 such that mod f of z less than or equal to 1, and let f from U to C be the map defined by f of z is equal to ei psi z minus a by 1 minus a bar z for a element of D and psi element of closed interval 0 to 2 pi. Which of the following are true? So we have defined here and map. We have to find which of the following options are true. So first of all, we'll look into the concept. F of z is equal to e per I theta z minus a by 1 minus a bar z maps is modulus z less than or equal to 1 onto modulus w less than or equal to 1. And this is a bilinear transformation. So bilinear transformation always maps boundary points to boundary points. That is mod z equal to 1 onto mod w equal to 1. And bilinear transformation is always a 1-1 map. Mod e per I theta is equal to 1 and modulus z by z bar, that is z bar conjugate of z, is equal to 1. So now we'll move on to the question. So they have given f of z is equal to e per I psi z minus a by 1 minus a bar z. So this is similar to this form. So it maps mod z less than or equal to 1 onto modulus w less than or equal to 1 and boundary points to boundary points. Also this is a bilinear transformation, so it's also 1-1 map. So the first option is asking like modulus f of e per I theta value. So I'll replace z by e power I theta. So this is equal to modulus e power I psi e power I theta minus a divided by 1 minus a bar e power I theta. Now I am splitting the modulus sign. So this is equal to modulus e power I psi modulus e power I theta minus a by 1 minus a bar e power I theta. So this value is equal to 1. So now from the numerator I am taking e power I theta. Now after that I am splitting the modulus. So we'll get this is equal to modulus e power I theta into modulus 1 minus a e power minus I theta divided by 1 minus a bar e power I theta. I have not written here but just calculated mind wise. So we'll get modulus e power I theta's value 1. So we'll get balance like modulus 1 minus a e power minus I theta by 1 minus a bar e power I theta. You see that denominator is the conjugate of numerator. So that is in the form is modulus z by z bar. So this value is equal to 1. So we got modulus f of e power I theta is equal to 1. Or else you can say z is equal to e power I theta. So when we take modulus, we are getting 1. We know this transformation maps boundary points to boundary points. So mod z is equal to 1. Therefore, f of z, that is mod of f of z is equal to 1. So now we'll check the correct options. So the correct options are 1, 2, 3 and 4. Next question, question 83. Let f from c to c be an entire function and let g from c to c be defined by g of z is equal to f of z minus f of z plus 1 for z in c. Then which of the following are true? So we are given an entire function f and g is defined by in terms of f. Then we have to check which of the following are correct. So first of all, we will look into the concept used. So identity theorem says that suppose f of z is analytic in D. D is like unit circle, and if the set of zeros of f has limit point in D, then f of z is equivalent to 0 everywhere in D. So now we'll move on to the question. So first question is like f of 1 by n is equal to 0 for every positive integers n implies f is constant function. So first of all, find the zeros of f, and 0 of f is happening like 1 by n, and the point 1 by n is converging to a point 0 and its 0 element of c. Therefore, by identity theorem, f of z is identically 0 everywhere in C. That is, f of z is constant function. So option 1 is correct. Now option 2, f of n is equal to 0 for all positive integers n, then f is constant function. Here 0 of f is equal to n and it is converging to infinity and it does not belongs to C. So we cannot say whether f is a constant function. So option 2 is wrong. If f of 1 by n is equal to f of 1 by n plus 1 for all positive integers n, then g is a constant function. So in the question they have given g of z is equal to f of z minus f of z plus 1. So I am replacing z by 1 by n. So we will get g of 1 by n is equal to f of 1 by n minus f of 1 by n plus 1. They have given f of 1 by n equal to f of 1 by n plus 1. So when we use that, we will get g of 1 by n is equal to 0. Now zeros of g is equal to 1 by n and it is converging to 0 and it's element of C. Therefore, by identity theorem, g of z is equivalent to 0 everywhere in C. That is, g is constant. So option 3 is also correct. Now option 4, they have given f of n is equal to f of n plus 1, then g is constant. So they have given g of z is equal to f of z minus f of z plus 1. So I am replacing z by n. So we'll get g of n is equal to g of n minus f of n plus 1. So f of n and f of n plus 1 is equal. So we'll get g of n is equal to 0. And the zeros of g, which is equal to n, it is converging to infinity and is not an element of z. So we cannot say g to be a constant function. So option 4 is not true.